Okay, so let's get started. Well, good morning or good afternoon and good night to everybody. It is my great pleasure to introduce you to Jinshuan Liu. She's an assistant professor here in Syracuse University from the Department of Mathematics. She's an expert in statistical analysis and causal inference, and she's a senior research affiliate in the Center for Public Research in the school too, in the university, sorry. Her research interests includes not just causal inference, but also semi-parametric modeling, high-dimensional data, measurement error models, and case control studies. She has a wide range of statistical consulting experiences in industry, nonprofit research industries, institutes, and academia. So without further ado, please go ahead, Jinshuan. Thank you for being here today.
Well, thank you for the nice introduction, Daniel. Hi, everyone. So let me share my screen now. Okay, so. Are you able to see my screen here?
Yes.
Okay, awesome. Okay. Full screen mode. Okay, so thank you for inviting me here to talk about causal inference. And today I will focus on causal inference for complex observational data. And here is a very brief outline of my talk. I will first give a general introduction of causal inference and then focus on the high dimensional issue in causal inference. After that, I will talk about another complexity in the observational study. To be specific, I will focus on the measurement error issue in observational study. Well, almost all of us ask causal question every day, but we may not realize it. Now, what is a causal question? So to sum up, a causal question is usually an action, or we call it a treatment, or some intervention. Will this kind of action or intervention will lead to another outcome? So in short, we can just write it as A.
Sorry, Jinshuan. I don't see the slides. I think I don't know if you have advanced in your slides, but I just see the first slide, the Adobe window.
Oh, let's see. Yeah, then probably let me stop and start again. Stop and share again. Okay, so stop. Okay. Okay. Stop sharing. Let me share again. So something goes wrong here. Okay.
Now we can see outline.
Okay.
Slide number 2. Yeah.
Okay. How about this page? Third page.
Perfect.
Okay. Sorry about that. So if we denote an action or a treatment using the notation A, and then using Y to denote as the outcome, then the relationship will be A cos Y. So this is a causal question we ask every day almost. So for example, some research study shows that sleeping on the back during late pregnancy will increase the risk of stillbirth. Now, can we make the conclusion that sleeping on the back will cause stillbirth? So this is a very interesting scientific question. If we are able to afford randomized experiment, then to address this causal question will become much more simpler. We can just simply randomize all the experimental unit into different treatment group, and then make sure that other than the treatment, everything, all the rest of the factor can be controlled or they are comparable. And then we will just examine the outcome. If there is a difference in this outcome between two treatment group, then we can draw the conclusion that, okay, that this kind of action or intervention will lead to the will cause stillbirth. But most of the time, we are not able to afford a randomized experiment due to so many issues. For example, you cannot force a woman to sleep on the back during late pregnancy. So most of the time we will have observational study. So if in randomized experiment, if we are able to quantify the average treatment outcome, say expected value of the outcome given one group of treatment, and then we just take the difference between this expectation between this group. However, in observational study, the difference between these two quantity does not necessarily means the causal effect. So that's not the average treatment effect, or sometimes we call average causal effect. Okay, so this is because we have some other control variable. So allow me to denote it as X. This control variable may also cause both the outcome Y and also intervene with the actions A. Okay, so that means it will confound with the cause and effect relationship between Y and A. Okay. So the crux of establishing a causal inference is called a ceteris paribus. So this is a Latin word. So it means holding all other factors fixed. So that means we are trying to make sure that everything except the treatment difference, everything except the treatment are the same. Okay, so that all the individual or all the subject in different treatment group, they are comparable. Okay. So in observational study, these conditions does not hold. So it has no guarantee that the change in the outcome Y is solely due to the treatment A. So that's what we are trying to, that's the challenge in observational study. Here, I will focus on the causal inference using the potential outcome framework. So this is a framework under Neyman and Robin's work in 1990s and 1974s. So under the potential outcome framework, we make a very common assumption. This common assumption assume that there is no unmeasured confounding, or we call that there is a ignorability in the research. Okay, so mathematically that means conditional on the covariate or control variable X, your outcome and the treatment will be independent. Okay, so this is what the no unmeasured confounding says. Okay, so under the potential outcome framework, there is a lot of method to draw the causal relationship, and among this method, most of them are based on propensity score approach. Now, what is a propensity score? A propensity score is actually a conditional probability of the treatment A given the observed covariate. So the observed covariate, like I denote earlier, we use a notation X to denote that. Okay. And then a propensity score, it's actually a balancing score. We call that a balancing score in the sense that if we are able to conditional on the propensity score, then the distribution of those measurable covariate, they are the same between the treated group and the untreated group, so that we can so that we can draw comparisons. Okay. So if we are able to adjust for the propensity score, then we are able to remove the confounding bias from the difference between this covariate. So this is a very well studied result from the Rosenbaum and Robbins paper in 1983. Okay. So that's the notion of propensity score. So under the potential outcome, most of the literature make two mild conditions. The first condition is regarding the propensity score. We call it a positivity. So a positivity assumes that the propensity score or this treatment probability of A given the covariate is bounded between 0 and 1. So this positivity will ensure that every individual will have a non-zero probability to receive at least one treatment or either treatment. Okay. And the second assumption is that we assume a consistency. Okay, so the consistency is about the outcome, why. Okay, so if one, assuming that we have a binary treatment, say A takes a value of 0 or 1, so that means either treatment 1 or treatment 0, then the person who received treatment 0 will receive an outcome y parentheses 0. And on the other hand, if a person receives another treatment 1, then the outcome will be y parentheses 1. And in this, in the observational study or in a randomized experiment, we can only observe either y1 or y0. We cannot observe both. So then we write the observed outcome y as this combination. So this is the consistency assumption in causal inference. Okay. Okay. And then a very popular estimator to estimate the average causal effect is using this inverse probability weighted estimator. So this estimator is a weighted version of the two different outcomes. So as we denote earlier, this A notation, that's the treatment, and then Y, that's the outcome, and then this pi I, that's the propensity score function. So this is a celebrity Thomas Harvey's estimator, which is first used for survey sampling. Excuse me, but it turns out that if we do this kind of weighting, we are able to estimate the average causal effect consistently. Okay. Okay. So now I want to focus on the data issue. So most of the time when we have the data, one aspect of the data is that we usually have large number of covariate. So if we have a large number of covariate, it is difficult to visualize or interpret the results. There's tons of methods to deal with high dimensional data, but all of these methods can be classified as two different approach. The first approach make the assumption of sparsity. So in sparsity, if we make a sparsity assumption, then we usually assume that there are only a few of the covariate have the explanatory power, and all the rest are just redundant. So if we make this assumption, we can handle the high dimensional data through variable selection. So this is usually done through some penalization. Another type of method assume reducibility. So what the reducibility does is that we assume only a few linear combination of many of the covariate are useful. So we try not to exclude some of the variable that may have the explanatory power. Okay. So if we make this assumption, then we usually analyze the high dimensional data through dimension reduction model, or we have a sufficient dimension reduction. So what is called a sufficient? What is called sufficient? So if we write the dimension reduction model as R of X, then if this dimension reduction model is said to be sufficient, if the distributions of the y, so that's the response variable, given this dimension reduction model is the same as y given the original covariate x, then we say that this is a sufficient dimension reduction model. Okay. Okay. So to be more specific, a dimension reduction model, we assume that the distribution of the outcome response y relates to the covariate x only through beta transpose x. Mathematically, it can be written in this way. So given the combinations of beta transpose x, this response is independent of x. Okay. So another way of writing this is that we can write this in probability. So the probability of y given x is the same as probability of y given beta transpose of times x for all the y's. So this is a typical typical dimension reduction model. And to be even more specific, this is actually a central space model. So in statistical literature, we write it as subscript y given x. So the goal is try to estimate or identify this central subspace. And then this central subspace is spanned by the columns in these betas. Okay. So now let's talk about the estimation in dimension reduction model. So like I said in the previous slides, our goal is to estimate the central subspace, which is spanned by this beta matrix, okay? And then the dimension of this beta is P by D, with the smallest D. So this smallest D, it is the smallest space in this high dimensional, I don't know how to call it. It's in this high dimensional structure. And then this D is uniquely identified, and it also exists according to Cook's literature in 2004. Okay. And in statistical literature, there are lots of methods to do the to do the dimension reduction, and all these methods can be grouped as three different approach. The first approach is called the inverse Bayes regression method. So here I list the three most popular one, and this slice inverse regression model, that's the very first method that deal with the dimension reduction. Okay, and there's a slice average variance estimation method or direction regression method. We call it DRs. Okay, and then the second type of method is called a non-parametric method. So I list two representative one. The first one is called density-based minimum average variance estimation. In short, that's called DMAVE and slice regression. Okay. The first type of method and the second type of method, they have their own benefits. So most of them are very simple, very easy to implement, but they rely on strong statistical assumption, which will bring lots of limitation when it comes to data analysis. So we propose a third type of method, which make use of the parametric method and the non-parametric method. So we call it a semi-parametric model. Okay. So today I will focus on the semi-parametric method, which does not rely on strong assumption. Okay. So to be specific, we are trying to implement this dimension reduction method to estimate the causal relationship in observational study. So our goal is a little bit ambitious. we try to come up with a method that does not rely on parametric assumption of the propensity score model or the outcome regression model. And we hope that the model or the method is data adapted and it can handle many covariates simultaneously. And we want the method can handle both continuous and discrete variable. And we do not need strong assumption on those we do not want strong assumption like the inverse Bayes method or the non-parametric Bayes method. So what we do is pretty simple. So in the method we implement here, we only assume that the treatment probability depends on the p-dimensional covariate vector, this X, only through several linear combinations of beta transpose X. So this will fall into the, excuse me. So this will fall into the category of dimension reduction model. And then what we do is we try to employ a non-parametric link function for this conditional probability. So this is the innovation part of our semi-parametric method. And then to be specific, what we do is we try to model the propensity score model using this flexible form. Okay, so we have the probability of A. If you remember, this is the treatment. Given the covariate X, or we call the control factor. So this is the conditional probability of an individual who receive a treatment. Okay. So this equals to the exponential form of this quantity over 1 plus the exponential of this guy. Okay. And then here, this eta, that's a arbitrary unspecified function. So we do not make any assumption on the form of this eta. Okay. And then this beta here, rather than just a vector, it is a matrix. It's a P by D matrix where the upper D block is identity form and the lower L block, it's an arbitrary matrix. Okay. So the problem becomes estimating the lower block of this B, so that's BL. If we are able to estimate this BL, then we will be able to estimate the propensity score. And then we can go ahead and calculate the average causal effect. Okay. So it turns out that this model is very flexible in terms of it's very flexible to take care of high dimensional data. Okay. Now you may wonder, how do we estimate this beta here? The next thing I will try to talk about the big idea of the estimation part, but I will skip many of the mathematical derivation. So we seek the we use the semi-parametric theory and use the efficient estimating function. Okay, so now what is the estimating equation for beta? If we want to seek the efficient approach, then we would need to derive the efficient score function. So the score function, if you take mathematical statistics, you know that once you have a model, you can just derive the score function. And then the efficient score, it is the residual after you project the score vector with respect of your parameter. So to be specific, our parameter here is this beta onto the nuisance tangent space. Okay, so the nuisance tangent space, the derivation is kind of technical. I don't want to bore you with math in the early morning, so I will put the detail in the paper. So if you are interested, I can send you the paper to that shows the detailed derivation. Okay, so after doing some serious math here, we arrive at this estimating equation for the parameter beta. Okay, so if we are able to solve these betas, then we will be able to estimate the propensity score. And that means we will be able to evaluate the causal effect, the average causal effect in these high dimensional settings. Okay. Now let's stare at this estimating equation for a second. So we see that this x, that's the data we observe, okay? And then this is the conditional expectations of x given beta transpose x. So this is an unknown quantity that we cannot have, we don't have access from the data, okay? And A, that's the treatment, which is observable. And another unknown quantity is this eta, the function. So that's the unspecified non-parametric function we in our original propensity score model. Okay. And then this eta prime, that's the partial derivative of this eta. If we don't know eta, we don't know eta prime either. So in this estimating equation, we have three unknown quantity. How can we estimate beta? So the next slides, I will talk about some strategy, how to deal with this one, two, three unknown quantity. Okay. So first, the conditional expectations of x given beta transpose x. So this part is relatively simple. We can just adopt some non-parametric local constant method, or we call it a Nadaraya-Wilson kernel estimator. So this is a very popular popular non-parametric estimator in statistical literature or econometrics literature. So this is a very standard form of a NW kernel estimator. So in this form here, this K of H, so that's the kernel function. And to be specific, the K here, oh, sorry, there should be a little H here, sorry. Sorry, this is a kernel function, and then this K here, that's the multivariate kernel function. And H here, that's a bandwidth. So like almost all non-parametric method, we always need to deal with the bandwidth selection. Okay. Now there's nothing tricky in estimating the conditional conditional expectation. Now the tricky part is how do we estimate this unspecified function eta and its partial derivative? Well, thanks to the way we model the data, we can derive a closed form estimation using some non-parametric kernel approach so that we are able to estimate this two quantity. So again, I will skip the math part and show you the final estimating equations. So these two ugly looking equations, they are the magic of solving this two unknown function or unknown form here, okay? So in this two equation, this little B0, so, and then this B1 transpose, these are the two quantity that represents the estimator of this eta and eta prime. So that means we are trying to solve these two sets of equation for eta and eta prime, okay? So you have, although you only see two of them, but actually it's 1 plus d of them. It depends on the dimensions of this beta, okay? So because this is the derivative of this eta, okay? So for example, if you have P, if you have if you have beta that has the dimensions of P by 2, then you have 1 plus 2. So that's 3 equation that solve 3 of this quantity here. Okay. So once you have the estimator of this eta and eta prime using this non-parametric kernel method, we can just plug them into this efficient estimating equation that solve for the beta. And then we replace the conditional expectation with the estimated version. So we put a little hat here. So now the efficient estimating equation for this beta, everything, all these are three unknown quantity. We have the estimated version to plug in. So we are ready to solve these betas. Okay, so you just solve the equation for parameter beta. Okay. So now here I want to show you some simulation results that compare the method we propose here with several existing methods that take care of that estimate the propensity score. So the first box plot, this is the true data form. That means we know all the we know exactly what the model looks like. So this will serve as the baseline. Okay. And then this eta star. So that's also this is also the method we implement in this method, but I did not talk about it because we have another better method, which is this eta hat. So this eta hat method, that's what I just talked about. So we estimate the conditional expectation non-parametrically and estimate the unknown link function eta and its first derivative non-parametrically. So everything is non-parametric. We actually do not make any assumption on it. And then this TMLE, it's called Targeted Maximum Likelihood Method. BRDR stand for Bias Reduction, Dimension Reduction Method. And then this is another double robust method proposed by researcher 10. And this is a typical logistic regression method on the propensity score. So it's a pure parametric approach. And the blue dashed line, that's the true average treatment effect. So from this comparison, we see that these are the last four methods. They cannot even capture the middle quantile. So this is the 25th quantile, 75th quantile. So they did not even capture the true average treatment effect. But if we look at the two methods we propose here, specifically the efficient method, this eta hat, we capture the true average treatment effect very nicely. Okay. Now compared to another method in our work, it also did a nice job in capturing the average treatment effect. But as you can see from the box plot, it has a larger variability. So that means it's less efficient compared to the efficient estimating, compared to the efficient estimator here. Okay. So in this first simulation, we actually assume that there's no dimension reduction available. So the smallest subspace D is the same as the number of covariate you have in the data. Okay. Now I want to show you a second simulation study that the dimension can be reduced to 1. So the data we observe is p-dimensional, but we are able to reduce the dimension to D. Okay. So again, we compare our method with some other existing method. So our efficient estimator consistently perform the best compared to all other existing methods. Okay. I want to pause a little bit here. Do you have any questions so far? Okay. Okay, so feel free to stop me if you have any question. So now I want to switch focus on another aspect in the complexity in observational study. So we wanted so we focus on the measurement error issue in causal inference. So we talk about the propensity score method, and this method relies on the correct specification of the propensity score modeling. So we need to have the correct form of the propensity score, and we need to include all the correctly measured covariate. So the first part of the talk, I focus on the correctly specified model. Now, the second part, I want to address the issue that some of the covariate are not able to measure, or they can be measured subject to some error. So the consequence of not being able to observe all the variable is that the no unmeasured confounding assumption does not hold. So this will break down the entire theory of the potential outcome framework. So let me define some notation before we go into the model. So assume that we observe the data with outcome Y and A against them for the treatment, and X and Z, that's the covariate. Here I break it into two notation because I want to separate the error prompt and the error-free variable. So X star here, that's the variable that we are not able to measure correctly, or it's subject to measurement error. And this Z is the error-free variable. Okay. And the good thing is that although we are not able to observe the correct form of X, but we are able to observe its surrogate version. And the relationship between the surrogate and the true variable is through this relationship. So we have at the error term, this U here, and a most popular assumption in the literature is that this U follows some normal distribution with um, some variance omega here. Okay. Now we slightly change the propensity score a little bit. So the propensity score now become this logistic regression form with beta transpose X. So, and then this theta plus some linear combination of gamma transpose Z. Okay, so again, this is X is some variable that may have contains a measurement error, and this Z is error free. So our goal is still to estimate these beta so that we can calculate the propensity score that allow us to establish the causal relationship. Okay. So if we directly use the error prompt covariate X star, then it will not take us anywhere to balance the underlying true covariate, so that it will not provide any accurate causal estimate. Okay. Okay. So what we do is we prescribe a bias correction approach. So to do this, we will need to need to do some derivation by deriving a complete and sufficient statistic for the true covariate X here. So we denote it as this delta. So this delta will serve as the best estimate of the true unmeasurable covariate, and then replace this delta um, um, and then use this delta to estimate the propensity score here. Okay, so then the propensity score after we do the bias correction will be looking like this. Okay, so again, I will skip the math derivation and then show you the final result of the estimating equation that can allow us to estimate the parameter beta and gamma here. So we implement this two estimating equation that solve for the unknown parameter. Okay, so in this two equation, they are not ready to implement yet because we have this unknown non-parametric link function and the conditional expectations of the two covariate given the delta and z. Okay, so if we use the definition of expectation, then we will need to know the two covariate x and the conditional distributions of x given delta and z. However, none of them are available. So our strategy is we directly propose a working model for this conditional expectation. This is doable because we have the nice relationship between the delta, which is the complete and sufficient statistic, and this x star. So we can derive the relationship between the expected value of x star given delta and z to be this form, and then the conditional moment of a given delta z can serve as a practical guide to choose a working model for this quantity. So the idea is simple, and and we also have a practical guide of choosing this model. So it's completely doable compared to you do a lot of the convolution of two unknown quantity. Okay, and computationally it's more efficient. Okay, and then to solve and then in this model to solve this unknown quantity here, we again try to avoid parametric assumption. So we solve them not using some non-parametric approach. So that means we are trying to implement this long, ugly looking formula to get the estimator of this theta 0 and theta 1. So that represents the estimator of the unknown function theta and its first derivative. Okay, so then after we have all these unknown quantities solved, we actually try to solve this equation and this two iteratively. So we use some profile likelihood method to solve this equation, so that our final product is beta and gamma, and then the propensity score. And the propensity score we denote it as this p hat. So everything is estimated. Okay, and then plug in to the average treatment effect estimator using the inverse probability based estimator, so that we can solve that quantity. Okay, so in the rest of the slides, I have several simulation study that shows the result. So I know I run out of time, so I try to be quick. So the first setting, we start from the similar case. So the true covariate x is some univariate form, and the amounts of measurement error can be low and high, so that we try to estimate its, we try to assess its performance and compare with three other existing methods. Okay, so this semi 1 and semi 2, these are our method. Okay, so why don't we just quickly look at the coverage rate? So when the amount of measurement error is small, say sigma of u is 0.3, then the other three methods, so the naive method, it's kind of just use whatever is observed, so it ignore the measurement error. And this RC means regression calibration. So we try to do some calibration on those methods, but we still make strong assumption that we know the true distribution, say normal or uniform. So when the amount of error is small, like 0.3, this method, it looks like their coverage rate seems okay. Okay, but when the amount of error increased to 0.9, this method immediately break down, and these two methods, they are not as good as our two methods. Okay, so and then the way we construct this coverage rate, it rely on two theorem we prove in our paper. So if you are interested, feel free to look at the paper I present here. Okay. So the second setting, we increase X to multivariate, and we also increase the dimensions of this error-free variable Z to 8 of them. Okay. So again, we compare the performance of these betas. So here you see the other three methods, their coverage rate, they are all below 90%. Okay, but our method, it consistently give us the coverage rate around 95%. Okay, so which is very good and what we would like to see. Okay. And three, so that's again, we make the data generating process even more complex. Okay, so let me show you the last one. Okay, so in simulation setting 4, we have the error prompt and error free covariate correlated with each other. So and then both of them are multivariate. Okay, and the degrees of measurement error, they can be high, moderate, and low. So now we compare their performance here. So the first three column result here, we look at the coverage rate. So the naive method can only capture about the highest amount is 86%. So 86% of the time it will capture the true betas. That's the best the naive method can do. And the regression calibration method. So if you quickly scan through of them, the coverage rate, the maximum one is only 89%. But our method, it consistently capture the true covariate. It consistently capture the true betas parameter around 95% of the time, regardless of what model we propose in the conditional expectations of X given delta and Z. Okay, so and then here is the final product of the average treatment effect estimation. So the last two, SEMIT 1 and SEMIT 2, that's our estimated for the average treatment effect. So compared to the other three methods, our method capture the true average treatment effect in all four different simulation scenarios. Okay, so that's the simulation results I want to show you. So allow me to quickly sum up what I just talked about. So I give a very gentle introduction about the causal inference and focus on the sufficient dimension reduction technique for causal inference and talk about the measurement issue, to be specific, error in the variable in causal inference. And here are the advantage of our proposed method. So I skip lots of technical details here. If you are interested, these two are the paper that my talk focus on. The first paper here, that's about the measurement error issue in causal inference. The second one focus on the dimension reduction that I talk about here. So if you are interested, feel free to look at this two paper. And then these are the key reference of the talk I mentioned here. Okay, so thank you for listening. Any question or comment? Well, here is my contact information. If you have any question or would like to ask me a question, feel free to send me email. Okay. Thank you.
Thank you, Chenjuan. Thank you very much. Let me pin you so we can both appear. Okay, so lots of applause in the little icon here in Zoom. So I don't know if there are any questions from the audience. There was a lot of discussion on the details on like regularization and different concepts in your presentation. And Hendrik is very graciously adding all the references to our Azoteron group. So anybody wants to ask a question, or I just...
Yeah, I saw
Oh,
there
sorry.
lots of message in the chat box, but
Yeah.
sorry, I did not look at that
Yeah,
during
that's
the
fine. So Julio asked if you will perhaps share the code of this method.
Yeah, the code. Sure. The code of the paper is actually online.
Okay.
Yeah, but if you cannot find it, feel free to email me and then I can send you the code.
Great. Thank you. And Sylvia has a question.
Yeah, I would love to know if anyone has used your method that you know of, and in which other contexts has it been used other than, I think it was like mainly medicine, what you were thinking of, right? Or, and yeah, just curious of
Well, thank you for
applications.
asking.
And thank you for your talk. As Hendrik said in the chat, it's like a summarization of all methods, so it was pretty cool. Thank you.
Well, thank you for asking. The method I talk about here, it actually has a very wide application. So as long as you have observational study and then your data is of high dimensional or suffer from measurement error, this method can be applied to analyze the data. So it's not restricted to say medicine data or social science data. It has a very wide application.
I was just wondering if you knew of concrete examples that someone has used, in which type of multidimensional data has it been used?
Yeah, so
Do you know?
the application we did for the high dimensional data is the healthcare data study. So we apply this method to some low birth weight data in economic study. So that data it has a, I think the number of observation is about 1,020 something, and number of covariate is about 50, and it has some categorical variable or continuous or binary things like that. Yeah, so our method work very well for that kind of data set. And the measurement error approach application, in the paper, we apply to a survey data that try to address the stroke recovery in the underserved population. So that data, I think the working example has 1,000 observation, but the number of covariate is about, I think 500, as I remember correctly, but I need to double check of that one. Yeah. Thank you for your question.
Thank you. Any other question? I have a question, Jin Xuan. So these, the non-parametric method you presented, one of the things that I was thinking is that maybe you need, what are the data requirements of such a method? It seems that it will need more data perhaps compared to a method that makes some assumptions. And yeah, and then I have another question, but I'll just ask that. What are the data requirements? How much it scales?
Okay, so to implement the non-parametric part in the data analysis, like the example I mentioned earlier, where we have about 1,000 observation and number of covariates is about 100 to 500. The method works well. But the thing is that just like all the non-parametric method, the non-parametric procedure, it takes a long time to run the procedure. because we do not make the assumption, and it needs lots of time to do the cross-validation in terms of tuning for the bandwidth. So that part takes a lot of time in terms of computing. Okay.
I see. And in terms of the coverage of the covariates, does it kind of automatically learns where, like, the two groups, it matches that the covariates are covered, like
The covariance.
The kind of the covariates of I don't know what the proper language it is, but once you do the propensity score matching, and if you look at the covariates, the X variables, how much they match between the control and the experimental units.
Well, that's a very important question. I know different area, they have a different terminology for the same thing. So here I use a covariate because most statisticians prefer to call it in that way. So to address your question, we try to avoid doing one-on-one match on those covariate, like X1 match X1, X2 match X2. But what we try to do is we try to match on the propensity score. So that means even though like we have 500 covariate, but what we need to do is we only match for the one-dimensional propensity score. And then we can do balance assessment before matching and then after matching. Okay, so that make the test much more doable and simple to handle. Yeah.
Okay, so it seems that there are no more questions. Thank you so much again, Jin Chuan, for coming to our little summer school. It was very interesting, your presentation. And we'll, for everyone, we'll make this available online. But I think some people would like to see maybe the presentation, if you have it available, if you can please share it with me later, perhaps to put it like the PDF or the slides or something.
Yeah, sure. Well, thank you for having me.
Thank you.
Okay. Bye, everyone.
Bye.
Thank you.